I continue from where we stopped. So previously we are handling how to name alkanones, and those are ketones. So today we are going to explore properties of carbonyl compounds. So we look at these are properties of carbonyl compounds. Carbonyl compounds. So there are two categories of properties of exploration. So one can look at physical properties of carbonyl compounds, and then we can also explore chemical properties of carbonyl compounds. Chemical properties of carbonyl compounds. So those are the two kinds of properties of exploration. So I want to start with the chemical properties. Chemical properties. Chemical properties of carbonyl compounds. So under chemical properties, just as the name sounds, these are chemical reactions. Chemical reactions of aldehydes and ketones. Chemical reactions. Chemical reactions. So before we dive into these chemical reactions, it is important. We have two classes of carbonyl compounds. We have aldehydes and the ketones. So it is important to first compare reactivity. Compare reactivity of aldehydes. Don't forget that aldehydes have a representation of R, CHO, and the ketones have a representation of R, CO, R prime. R simply represents an alkyl group or hydrocarbonic group, for example, benzene ring, aryl group, alkyl group, or aryl group. For aldehydes, R can also be a hydrogen atom, so that you come up with the methanol. So what are the key takeaways under this? So we want to look at these two classes. We want to look at these two classes of carbonyl compounds. Then you compare the rate at which they react. Don't forget that both classes, both of them, they are generally made up of this group in black, the carbonyl functional group. And if we are to discuss their chemical properties, basically we are dealing with reactions of this carbonyl functional group, meaning that there are some reactions. We are going to see that there are some reactions which are undergone by the two classes. And therefore, since we have reactions that are undergone by the two classes, by the virtue of the fact that both of them are composed of the carbonyl functional group, it is important to explore how the two classes will behave towards those reactions. In simple terms, what will be the rate of reactivity of the two classes? So I want to claim that aldehydes are more reactive. I want to claim that aldehydes are more reactive than ketones. towards nucleophilic addition reactions. Towards nucleophilic addition. Sorry. So aldehydes are more reactive than ketones towards nucleophilic addition reactions. Now this is a new term, a new word. Nucleophilic addition reactions. So what do I mean by nucleophilic addition reaction? Aldehydes are more reactive than ketones towards nucleophilic addition reactions. So by nucleophilic addition reactions, basically I mean, in a basic way, basically these are reactions. These are reactions undergone. These are reactions undergone by compounds. Reactions undergone by compounds made up of carbonyl functional group. So previously, under hydrocarbons, they explored reactions of alkenes and alkynes, and you were able to classify them as the electrophilic addition reactions. So if we are commenting about electrophilic addition reactions, those are reactions in a basic way. Those are reactions which are undergone by alkenes and alkynes. That is the basic interpretation. However, there is a technical one. Then for benzene and the other arenes, those compounds undergo electrophilic substitution reactions. So if we are discussing about electrophilic substitution reactions, those are reactions that are simply undergone by derivatives of benzene, including benzene itself. Therefore, for nucleophilic addition reactions, basically these are reactions which are undergone by compounds made up of the carbonyl, which have the carbonyl functional group. However, technically, by definition, just as the name sounds, nucleophilic addition, this is a reaction where a nucleophile is added. A nucleophile is an electron-rich species. Anything that has electrons, anything that is rich of electrons, we call it a nucleophile. So if I said nucleophilic addition, this is a reaction where an electron-rich species is added. So reaction involving addition of an electron-rich species to the compound. So technically, by definition, a nucleophilic addition reaction is a type of organic reaction, that involves addition of a nucleophile. A nucleophile is an electron-rich species that involves addition of a nucleophile to the carbon atom of the carbonyl functional group to form a single product. So it is a type of organic reaction that involves keywords addition of a nucleophile. What's the addition of a nucleophile to the carbon of the carbonyl functional group to form a single product? And I want to illustrate what I mean by that. So we have explored the fact that carbonyl compounds, both aldehydes and ketones, undergo nucleophilic addition reactions. And these are reactions where a nucleophile is added to the carbon of the carbonyl functional group. Now we have to explore how this occurs. How do nucleophilic addition reactions occur? So basically, we have said that this is a reaction where a nucleophile is added to the carbon of the carbonyl functional group. So we need an illustration of this. So this is the illustration of a nucleophilic addition reaction. So it is a reaction where the carbonyl functional group with this representation, carbonyl functional group reacts with a nucleophile. So Nu is representing a nucleophile, the representation of a nucleophile, and then I also have the carbonyl functional group. So I have said in this type of reaction, a nucleophile is added to the carbon of the carbonyl functional group. In simple terms, I want to add this to this carbon atom of the carbonyl functional group. That's what I want to do. But remember, Nu is electron-rich. So if it is electron-rich, it must serve electrons to something which is electron-deficient. It does not easily add to things anyhow. What induces its addition, there must be something which is electron deficient. Now, if it is available for it, it is able to donate its electrons to that thing which is electron deficient. Therefore, we have to first create something which is electron deficient so that a nucleophile is added. So what have we said here? We have said that in carbonyl compounds, the carbon atom within carbonyl compounds is electron deficient. This carbon here you see is electron deficient. Why? This double bond is the center of high electron density. Moreover, oxygen is more electronegative than carbon. So oxygen has a tendency of attracting bonding electrons towards itself. As a result, it acquires a partial negative charge, so that carbon has a partial positive charge. I have said the reason that's why we have this arrow is simply because oxygen is more electronegative than carbon. What I mean by saying that it is more electronegative than carbon, it has a higher tendency of attracting bonding electrons towards itself. So as a result, the electrons which are in this double bond are always directed towards oxygen. Therefore, oxygen attracts them, and that implies that it will acquire a partial negative charge and leaving a partial positive charge on the carbonyl carbon, meaning that this carbonyl carbon is now electron deficient. It is electron deficient, it needs electrons, and this nucleophile is electron rich. Therefore, it can donate to the carbon atom. So what have we said here? We have said that the carbonyl carbon has a partial positive charge. I am saying that the carbonyl carbon is electron deficient in simple terms. Why? It is electron deficient because it is bonded to a highly electronegative oxygen atom. What do I mean by saying that the oxygen atom is highly electronegative? I simply imply that the oxygen atom has a tendency of attracting bonding electrons towards itself. And once it attracts bonding electrons towards itself, it acquires a partial negative charge Once it acquires a partial negative charge, it leaves a partial positive charge on the carbonyl carbon atom. Now that the carbonyl carbon atom has a partial positive charge, that makes it prone or susceptible towards nucleophilic attack. Therefore, a nucleophile simply attacks. Here I have been able, in this statement, I have been able to explain why aldehydes and ketones undergo nucleophilic addition reactions. What have I said? It is simply because within them, they are made up of this carbonyl functional group. Carbonyl functional group, and the carbon to oxygen double bond is polar. The carbon to oxygen double bond is polar. What I mean by saying that it is polar, it is simply because we have difference in the charges of the bonding atoms. One atom is more electronegative, can take electrons, so that another one becomes electron deficient. So therefore, that one which is electron deficient can easily accept electrons. So once we add electrons, once the nucleophile attacks, we shall have the following. Have our C. This is now a single bond because one bond has been broken. Single bond with oxygen, which has a negative. Now that negative corresponds to breaking of one bond, corresponds to the electrons which were originally present in one of the bonds. And those electrons are being directed towards oxygen. So oxygen acquires a full negative charge. Then this carbon atom bonds with Nu. And Nu had electrons. It has donated them. So it is electron deficient. It has a plus. So that's what we mean by nucleophilic addition reaction. So what have I been able to do in this session? I have been able to highlight, don't forget, I have been able to highlight that aldehydes are more reactive than ketones. However, for that, I haven't explained that. I haven't explained why aldehydes are more reactive than ketones. That's where we are heading to. They are more reactive than ketones towards nucleophilic addition reactions. I have defined a nucleophilic addition reaction. Then I have also explained why aldehydes and ketones undergo nucleophilic addition reactions. Then I have also illustrated what I mean by nucleophilic addition reaction. So in the next session, I am going to explain why. I'm going to explain why. Maybe you can also think about it. I'm going to explain why aldehydes. Why aldehydes are more reactive. Aldehydes are more reactive than ketones. More reactive than ketones towards nucleophilic addition reactions. Nucleophilic addition reactions. Yeah. So this is our next session of exploration.